Welcome to Drone Systems and Control course. Today we are going to talk about Kalman filtering techniques. Okay. In the last lecture we discussed about parameter estimation and state estimation, why filtering is important. We will go a little more detail into understanding how we can estimate the states of the system which is changing with respect to time, and how do we derive and implement the Kalman filter. We will also get understanding between the prediction and correction steps in an intuitive manner. We will apply it to drone tracking as well as for drone navigation application. Finally, we will look into MATLAB implementation, where we see how we can design a Kalman filter specifically for 2D tracking problem, and how do we tune the parameters. Okay. It's just a recap. We look at why not raw sensors. We discussed this point in the previous lectures, but we am just providing a recap here again. The noise and disturbances are key. Every sensor, if real sensor, if you look at it, has its measurement noise. I have already mentioned that if you are looking at a height sensor, right, there will be a noise in measurement. In addition to the bias in sensor will also come into picture, the way it has been mounted, and those will also add a bias to it. We talked about different performance measures of sensors, how it will influence, how to select the sensors, right. So, these sensors will have a noise, and external disturbance will also cause measurements error. For example, if you are looking at a GPS position, it fluctuates, right. Sometimes the error will be plus or minus 1 meter if if you do not have a cloud cover, but the same error can go from 3 meters to 10 meters, depends on where the sensor is located. If you are having a multipath, or if this cloudy, again your error will increase, right. Now, raw sensors will values jitter and can be trusted for a control and decision making purposes, right. And you also have a problem of drift over time. I talked about this when we talk about selection of sensors, the internal sensors which required to measure the states of the system. For example, an inertial measurement unit, 6-axis inertial measurement unit or 9-axis. You have a 3 gyros and 3 accelerometers measuring x, y, z, right, and the attitudes of the drone. If you are trying to use them to estimate this attitude and the position and velocity, they start drift over a time. Suppose if you are using a robot, it is not relevant to the course, but if you just think about it, if you are using a wheeled robot and you are trying to get the encoders, again what will happen is the actual position, right. You need, if you want to control the steering very precisely. All these will drift, makes it long term localization becomes unreliable. If you are talking about autonomous system, right, autonomy is a key. When you are talking about autonomy, localization is a very important problem. How do we localize my position? Then only navigation becomes easier. Goal position is known, I need to know where am I, then only I will be able to navigate. So, drift will cause long term localization problem, and eventually reaching a goal will become very difficult. The other issue comes in, some of the sensors have low update rate or latency. For example, GPS is about 1 Hz. Suppose if you are using camera based navigation system, then you have a frame rate which comes into picture, and on top of it, if you are using a deep learning AI based solutions, and the number of frames that you can process per second do influence the measurements rate, right. So, the delay or some frames are not usable, then dropout will reduce responsiveness in real time systems. Sometimes you do not even get the complete view, right. Single sensor may not observe all state variables. For example, you just use accelerator alone to get the position and velocity, even though integration, the bias and drift will cause a problem, right. In addition to all these, the nonlinearity and bias is a critical. We talked about it, magnetometer, thermistors are nonlinear and bias. For examples, I am just talking about the real values, the raw values must be interpreted in the context of the system rather than whatever the current value that we are observing from the sensor, right. So, get a motivation in real world application. True states like position, velocity if you are talking about a thermal system, the temperature, even for a drone, if you look at the temperature plays an important role if you want to minimize the drift, right. So, I need my IMU controlled, temperature controlled, so that my measurements are more accurate, right. These are not directly observable. In such cases, we need the direct observation, we need the estimation so that we can control the systems. We mostly rely on noisy sensors, inaccurate models to estimate these hidden variables. Kalman filter provides a recursive, real-time, statistically optimal way to estimate these hidden states, right. For example, in multi-copter system, right, we integrate inertial measurement unit, IMU's data. We also combine with the visual odometry or camera, or what I meant optical flow sensor, which can be used to collect the data. Sometimes we can use barometer or LiDAR or radar to get my height, and I can combine all of this to get my states of the system. Kalman filter combine these to track 3D pose and velocity of the vehicle, essential for stability and navigation of the multi-rotor system, right. Kalman filtering is at the core of intelligent system because it gives me estimate of the state of the variable, a state of the system or state variable, and that will be used to control and navigation of the system. Kalman filter enables machine to make sense of certain uncertain world, right. So, what we have, we can use this for mobile robot. I can combine odometry, LiDAR, and I can get a 2D localization. I can also get the heading. In case of multi-rotor system, I can combine IMU, GPS and camera to get the 3D position and velocity. Now, let us look at what is this estimation problem is. Estimation in dynamical system in particular, right. In many engineering system, true internal state of the system cannot be directly measured. So, we need to have estimator. We can have a mathematical model that predicts how the system evolves, or we can have a sensor that provide noisy indirect measurement observation of the states. What is my goal? Estimate the true state using model and measurements. What is my objective here? Estimate the hidden state xk at each time step k based on the model, how we think the system behaves, the measurements, what our sensors observe, the inputs, the commands or external force applied on the system. Let us look at a generic system. Let us look at the process equation of the system. In a nonlinear system, x dot is equal to f of xu. The measurement equation, z is my measurement, which is again a nonlinear function of the state x and input u, right. If I linearize this system, I can represent about an equilibrium point. The process equation can be represented x dot is equal to ax plus bu. The measurement equation can be represented as z is equal to hx, right. Now, if I discretize the system, continuous system, and represent in discrete form, xk is axk minus 1 plus buk minus 1 plus wk minus 1, right. I am just representing in this red, I will explain it a little later. The measurement equation zk hxk plus vk. What are these variables? Xk is a state vector. For example, it could be a position and velocity. Uk is a control input, external control input. Zk is a measurement what my sensor sees. Wk is a process noise. I am assuming 0 mean variance of q, q is a process noise covariance, right. Vk is again a measurement noise. We are assuming that it has a 0 mean and covariance R, R is a measurement noise covariance, right. What are we seeing? Different aspects of it. The process noise and measurement noise. Process noise talks about uncertainty in the system. What are the sources for this uncertainty? It could be coming from model mismatch, it could be coming from external forces, it could be coming from system noise, or it could be due to approximation errors, right. assumption here is all of these are Gaussian in nature. I mentioned earlier 0 mean and covariance of Q. If you look at a measurement noise, right, it is uncertainty in the sensor measurements. It could be coming from sensor limitation, it could be due to quantization, it could be due to electronic noise, it could be due to environmental interference also. The assumption again, the measurement noise has a characteristics of Gaussian. Now let us look at the idea of a Kalman filter, right. The Kalman filter gives the clearest possible picture of the system's hidden state, right, even when your data is messy or incomplete. When I say messy, it is noisy, right. What makes it powerful? The estimates are recursive, no need to store the full history, automatically balance the trust between the model and measurements, works in real time with the fast efficient updates, provides confidence in the state estimate, optimally balance uncertainty. Kalman filter is an optimal solution under linear Gaussian assumption, right. Now let us look at how the Kalman filter loop is, or look at core workflow of the Kalman filter. It works in the principles of predict, update and repeat, right. At each time step, the Kalman filter performs two main operations to estimate the system state. One is the prediction step, the other one is the update step. So use the system model to predict the next state and uncertainty, estimate the next state before the new measurements arrives, right. So the state prediction x hat of k minus 1 is A, x hat of k minus 1 at k minus 1 plus B uk minus 1. The covariance also we need to be predicted, how the state covariance changes, right. Pk k minus 1 is A p k minus 1 k minus 1 A transpose plus Q, right. What it does? It projects the previous state forward in time using the system dynamics, grows the uncertainty based on the process noise Q. The update step, it is a measurement correction, refines the prediction using actual noisy measurement Zk. So innovation, that is a measurement residual, Yk is Zk minus H xk minus 1 k minus 1. This innovation Yk is a bridge between the prediction and update. Innovation covariance Sk H pk k minus 1 H transpose plus R. It filters how wrong the prediction was and guides the correction. And we need to do compute Kalman gain, k is Kalman gain at time step k. It depends on pk k minus 1 H transpose Sk minus 1, right. Upon computing the gain, we update the state estimate xk at k is depends on xk k minus 1 plus Kalman gain at k times Yk. Yk is the innovation which is bridging the gap. I use that information to update my state. I also update my covariance. Pkk is I identity matrix, Kalman gain kk H whole bracket times pk at k minus 1. So I am updating the covariance, I am also updating my estimate, right. What it does? It corrects the predicted state using the measurement data, reduce the uncertainty by balancing the model and sensor reliability, right. So if you want to read more about Kalman filter design and you want to understand in details, you can look at the book Optimal State Estimation, Kalman, H infinity and Nonlinear Approaches by Dan Simon. It is a very interesting book. Now let us look at how this Kalman filter works, right. There is an initial condition and based on that I am just doing a prediction, and then innovation sequence happens, Kalman gain computation happens, then correction or update take place, and then you move on to a new step, right, k. What is the intuition behind this Kalman gain, right? The Kalman gain K determines how much the filter should trust the new measurement versus its own prediction, right. It is the weighing factor in the correction step. If your model is trusted more, then the Kalman gain is small and small correction will take place. If your measurement is trusted more, the Kalman gain is large, larger correction will take place, right. If you see Kk, it depends on predicted uncertainty Pk k minus 1 H transpose H Pk k minus 1 H transpose plus R whole inverse, right. So, the Kalman gain adapts over time. So, it shows every time steps how much to trust the model or how much to trust the measurement at that point of time. Okay. Now, let us look at process noise presented drones or multi-rotor systems, right. Wind gust, right, sudden lateral drift will take place. So, the state prediction becomes inaccurate. Motor nonlinearity comes into picture, right, that results in variation in thrust. Instead of putting it motor nonlinearity, I would call it as a propulsion system itself, right. Electronic speed control system, motor plus your blades combined together, that will result in variation in thrust. The thrust model error leads to wrong acceleration. Actuated delay, right, there could be a lags, servo lags or electronic speed control system lags, that will result in improper measurements, right, control command not applied instantaneously. Simplified models, ignoring drag or vibrations, state estimate drift due to unmodeled effects. These are some factors which we need to keep into our mind. Kalman filter effect, understanding Q, right, the filter trust incorrect prediction too much and that will result in divergence, right. So, now let us look at effect of the process noise on Kalman gain. So, what is Q? Q is our design parameter, right, for the filter design parameter. Q models uncertainty in system dynamics, basically it looks at the process noise, right, represents things like model inaccuracies, external disturbances and unknown forces, right, which we are not taking into account in the model. How it affects the Kalman gain filter loop? In a prediction step, if you look at Pk, A Pk minus 1 K minus 1 A transpose plus Q, right, this is will affect my Pk prediction. Higher the Q means less confident in your model prediction. This leads to Pkk minus 1 which in turn increases the Kalman gain, because Kalman gain is directly depends on Pkk minus 1. Higher Q, larger Pk, which means high Kalman gain. What is high Kalman gain means? Trust the measurements more, means quick adaptation to newer data. Lower Q, a small Pkk minus 1 which means low Kalman gain. What does it mean? I trust the model prediction more, slow reaction to measurements, right. So, you need to understand what is the system, what is the state we are measuring, how we are selecting the Q and its influence clearly. I just did a small simulation to show the effect of Q on Kalman filter responsiveness. I am looking at the position of the drone, right. The black line is the true position of the drone. The red dots are my measurements, what is available. You can see the measurement is noisy. Then if I use a high Q estimate, that is green color, you see how the estimated state goes. If I use a low Q estimate, you see what is happening, right. So, you have to understand the relationship between measurements and this effect of design parameter Q, right. What are the tips? How do I select the Q? Q adjusts how responsive or how inertial your Kalman filter is, right. High Q reacts quickly, more noisy. Low Q, smoother but slow response. Now let us look at some other sensors and their noise measurement noises, right. GPS, multipath comes into picture, poor signal comes into picture. Suppose you are flying in between buildings, right, you will have multipath, and sudden climatic change will also provide poor signals, right, or you are flying below the canopy, again poor signal will come into picture. This will lead to jittery or delayed position fix. IMU, there is a vibration in the drone. Let us say suddenly there is a the motor mounting, there is some screws are loosened due to some wind effect or even over a period of time, right. That leads to vibration, and that vibration will also cause problems in your measurements. Temperature drift will also cause noisy velocity and orientation data. Magnetometer, electromagnetic interferences, you are flying closer to power lines, then you will have inaccurate heading, or you are flying indoor or in urban area. Barometer, pressure fluctuation will lead to noisy altitude in wind or indoors. Camera, we use camera sometimes for optical flow measurements. The motion blur or low light will lead to low pose from visual odometry. How does it affect Kalman filter? Understanding R, the process measurement noise, right, it overreacts to noisy sensor, start oscillatory or erratic estimates. Now let us understand the effect of measurement noise on Kalman gain, right. What is R? R represents sensor noise, how much you trust your measurements, right. How does it R appear in Kalman gain formula? Kk depends on Pkk minus 1 H transpose open bracket H Pkk minus 1 H transpose plus R, right, the whole inverse. Now let us understand how does the R affects the Kalman gain. If you understand how does the R affect Kalman gain, you know what is that effect of Kalman gain on state estimate, right. If high R, unreliable sensor, which means small kk. Low R, reliable sensor, which means large kk. Intuition, right. If high R, measurement is noisy, do not let override the model too much. Low R, measurement is precise, let us heavily correct the prediction. Again I did a small experiment, same for the position sensor, right. I have the black line representing the true position, red cross represent the measurement data, right. The blue line is the low R estimate, the green line is the high R estimate, to give an understanding of effect of R on estimation. Now let us look at one dimensional tracking problem. Okay. I want to track one dimensional position basically of the object moving with a constant velocity using noisy position measurement, right. My state is the position velocity, motion model is constant velocity. What is my sensor? Measures position, it is noisy, right. I am measuring my position, the actual trajectory is given in the black line. I have measurements which is represented in the red cross marks, the estimate positions are all given in the dotted line, right. Now look at the constant velocity, I am moving at 1 meter per second, right. You see the estimates how it is happening. Kalman filter struggles with drone velocity estimation. Problem here is velocity is not measured directly. Most drones only measure position via GPS or vision or acceleration informations. Velocity must be inferred, not directly observed, right. Kalman filter relies heavily on accurate measurements. Without direct velocity measurement, the estimate relies on differentiating the position or integrating the acceleration. So, if you differentiate, noise will get amplified. If you integrate, start drift over time. Let us look at another example. I want to do altitude control, height control system. I want to estimate my height and vertical velocity, right, with the time varying internal conditions of the system. I want to estimate Z over time, how it is evolved dynamically. I have a sensor measurement, I am using a barometer as well as IMU, and use an estimator to get estimate of the altitude in real time, that is Z dot is Vz, Vz dot is kt omega square by m minus g. My state vector here is Z and Z dot. Okay. I am having a measurement, I have a noisy barometer reading Zm, state being estimated or altitude and its velocity. Just gave an example, I am just trying to decrease my altitude, right, over a time, or increasing my altitude, right. I am trying to see how my velocity is being estimated during that time. Now let us look at a yaw control, right. Estimate the current yaw angle and angular velocity during the flight. What I want is psi and psi dot. I have a gyroscope measurements from IMU which will give me a xi dot. Magnetometer will give you the yaw angle with respect to the true north. These sensors are noisy, can drift, right. I am using an estimator. Here I am using extended Kalman filter. We will talk about extended Kalman filter in the next lecture. We use the angular kinematics, we use a measurement gyro and compass, we get the state psi and psi dot, right. How heading and rate is estimated. Just giving you a sample measurement from the actual experiment, right. We do a true yaw, right, and we have the compass, we have the estimated one, and we have the yaw rate, right, and how the estimated one, how close it is with respect to the true value. Now let us understand how high or low Q in these estimates, right. If a Q is too low, it becomes underestimated. What it happens? It filters the trust models too much. Ignore the real disturbances that happens due to wind or sluggish corrections may diverge. How do I diagnose this, whether I am going in underestimation or not? Large innervation residuals comes into picture, that Y will become very large. Poor tracking in disturbances, when you have atmospheric effects comes into picture, when there is a disturbance, wind disturbance and all, the tracking performance of the drone will be poor. So, you can make out from there. Sometimes you may have a delayed response. The drone will start reacting after the disturbance. You will be able to make out that your Q is too low. What do? We increase the relevant Q entries such that we can get a better estimate, responsive, right, and we can look at the flight logs to adjust the Q for flight modes, right. Let us say if a Q is too high, which means overestimated system, filter too uncertain of the prediction, jumpy, noisy state estimate comes into picture. You will see excessive correction from sensor updates, right. Estimated states fluctuate a lot. What you can do? You can reduce the Q gradually, validate with a smoother position and velocity plots. R is too low, over trusting the sensors, right. Filter overreacts to noisy measurement, noisy or oscillating estimates comes into picture. Estimate spikes when the sensor is noisy, state follow the sensor noise too closely, right. So, what do? We increase the R entries, add sensing filter, you can add a external filter to your sensor, right, verify sensor noise, from your log. R is too high, under trusting your sensors, filter ignores sensor input, slow convergence will be there, may not correct for the drift, long time to stabilize, estimate follow model not reality. So, what do? We decrease the R carefully, cross check with sensor specs or covariance of the actual reading. Now, let us understand some limitations of the Kalman filter. What are the assumption we are doing? Assumes linearity. Kalman filter assumes both the system dynamics and observation models are linear. It fails when applied directly to nonlinear system, right. Gaussian noise assumption assumes both process and measurement noise are zero mean Gaussian. In real world, noise may be non-Gaussian, there could be outliers, there could be bias, there could be multimodal. Non-Gaussian noise will leads to poor filtering performance. Number 3 requires accurate system model. Kalman filter is model based filter, right. It requires accurate knowledge of state transition model A, measurement model H and some noise covariance Q and R, right. Model mismatch leads to divergence or slow convergence. The fourth point is sensitivity to initial estimate. The initial guess for initial point x0, a state at 0 and p0 can impact early performances. Bad initialization, it take long time for convergence or filters instability. Fixed noise assumption. Noise covariance Q and R are typically assumed constant. In reality they are not constant, right. Noise vary with time as well as system states. One fix we can bring it in, we can bring adaptive Kalman filter methods that tunes for Q and R on online. Computational cost for high dimensional system, right. Kalman filter involves matrix inversions and multiplications. The computation can be expensive for large system, large order of the system. It is not ideal for real time on low power embedded hardware without optimization, right. You need to have reasonable computational capability to get this matrix computation done in very fast. So, I would like to summarize this particular lecture. The lecture focused on state estimation for linear dynamic system. We talked about Kalman filter as an estimator for linear dynamical system, how state and update equations for Kalman filters and intuition of Kalman filter gain, what is its effect, right. We looked at the influence of process and measurement noise covariance on Kalman gain, and we looked at the example with a multi-rotor system, the drone system, right, estimating the altitude, yaw rate and position, and we discussed on the limitation of the Kalman filter. What we will do now is we will look at some MATLAB demonstrations before I talk about some reference materials, right. Now, first let us look at Kalman filtering, right. So, if you see the state estimator, see this is a example how to perform Kalman filtering in MATLAB. Okay. How do we same equations we talked about, the only difference is here we talk about n plus 1 because it is easy with respect to the programming perspective. We talk about x n plus 1 is a x n, b u n and g w n, right, and you have y n is a measurement. Again it has an effect of I am taking a generic system where output is also depends on input, but in a multi-rotor system when we look at it u is not going to directly affect my measurements. So, we can look at the time update, we look at the measurement update, right. So, we can take a simple example to do a designing of the filter, right. Let us say I have a state matrix given here. My input B matrix is also given, my measurement is given, state 1 is my measurement, right. So, I create this equation xn is equal to a b, I have all this, right, and yn is equal to c xn and vn is my measurement noise, wn is the process noise, right. I can look at the time update and I can estimate the complete state of the system and as well as y. I can set the filter to create the plant model to input, and as well as -1 remarks a plant as a discrete or it is continuous, right. So, I put Ts is -1, which represents, you can see here, this represents the system as discrete. I can create the system dynamics, right, and then I can define what is my Q. Q I am just defining as 2.3, R as 1, then I can define Kalman system with system equations Q and R. I can get the respective state and x hat, right. I can use this filter to design any plant. I can give the input U W, which goes through the actual plant, I get the measurement, right, and the measurement goes in, I add the sensor noise to the measurements, and that is a noise which I am passing on to the filter. I am giving the input as it is to the filter, I get the true y hat as well as yt, right. So, I can get all these defined clearly. I can look at the time to which I want to simulate based on the data what we have. I am assuming input to be a sine of t by phi, right. I am giving a noise model, process noise, I am using W, which is square root of Q, and then I am putting a random number, right, and V also I am doing it with this, with the random number, right, and this is my noise. Now, with that I can simulate the response of output, and I have the yt, I have the ye, the filtered response, and I am adding that to get the measurement response. Then I can simulate exactly what is the true value, what is the filtered value, right. I can look at the error also, right, true measurement, filtered measurements, how does it look like, right. So, I can get this clearly. I can look at the time varying filter also here if you wanted to add the other effects and study, right. Now, this we can use to design directly and estimate the states. So, I thought I will just show you another example on how the state estimation can be done. In the lecture I just talked about 1D problem. Now, I thought I will bring in a 2D targets using linear Kalman filter tracking KF, right. So, I can initialize the model here, right. I am bringing in model, I am looking at the discrete time. So, what is my sampling time? dt is 0.2, the simulation time is 20 seconds, right. So, I get the entire time span and I initialize the true state, right, 32 and 40 and 2. Basically, I am talking about the initial position is a 2-dimensional plane 30, 40, that is x, y. The velocity in x is 2, velocity in y is also 2, that is my initial state. I am adding a process noise, right, where it is going to be added. Then I am doing a measurement noise and get the noise matrix, right. So, rest is like I am set the number of steps, true states, we have 4 states here, right, and I am trying to get the state estimates. So, I am defining the matrices what is required F and H, right, and then I can go on to look at the Kalman filter design as we explained in the previous MLX file, and then I can run and get the estimate, right. So, you will be able to see you can do the 2D estimation, it is pretty straightforward once you know the linearization done for your nonlinear system, and if you have the A matrix, B matrix and C matrix, and if you have an idea about how your sensor noise is going to be, and you can initialize the respective P and Q, right, then we can get the filter done, okay. So, you see here my y and how my estimates moving along with respect to my measurements. Okay. Now let us look at how do we tune the filter to improve the state estimation, right. Let me so we can bring in the test trajectories, we can talk about how the trajectories are going to be, and we can see how the position and velocity estimates vary with respect to time. Let me move this. Okay. So if you see my y position, right, during training what I have used when I tested what is my position with respect to x, right, I am trying to move like this. I am setting up the Kalman filter. We talked about this. There are 4 states here, x position and y position, x velocity and y velocity. I am talking about state covariance matrix, and I am talking about motion model, right, constant velocity model, and process noise is 2 cross 2, measurement noise is 2 cross 4, right. I am setting up the simulation. I can do the conversions whatever needed here, and then I can choose the initial conditions based on where the starting point of the system, right. I can choose the process noise. I can define the variance what I am looking at based on the data, and I can initialize how much noise I want in the beginning. I can also initialize R, right, and then I can look at how do we get the filter design, how the filter noise coming in during the test data, training data, how do we tune the filters when I trying to plot, right, how this RMS position error comes down on during training and testing phase, basically how I am going to adapt these values, right. So we talk about, we can also look at automated tuning mechanisms. If you do not want to do manually, when you tune, you get an understanding between the relationship between sensors and estimate how slow, how fast, based on that you can correct. You can also use auto tuning mechanisms which is present in MATLAB. I am not going in details, but these files will be added in our folder, you will be able to see it. Just give a glimpse of how this how we can minimize the residual predictions which we talked about in the beginning. How do we look at the parameter vector to noisy matrix conversions, how it will influence, how the prediction error can be minimized, is all available. We can use this to design appropriate filters and understand the effect. Once we have it, we can integrate this into our actual system and use it for control and navigation. Now going back, so these are the reference books: Optimal State Estimation, Kalman, H Infinity and Nonlinear Approaches by Don Simon, Kalman Filtering, Theory and Practice with MATLAB. This is also a good book, you can just read through, right. If you want to understand more about Kalman filter, how to derive these equations and what are the effects, various examples are available here. It will help you a lot in understanding. Thank you.